In this problem, we have a graph of function f. We know that g is the integral from 1 to x of f of t dt. The graph consists of lines, and this one is a quarter circle, and those are lines. We need to find the average rate of change, the instantaneous rate of change at a certain point. We need to figure out when graph of g is concave up, and we need to figure out all the x values where g has a critical point, explain whether those are local max, local mean, or neither, and justify the answers. Always justify. Let's start with question A, the average rate of change. That is our slope formula. So we need to calculate g of 5 minus g of negative 5 over 5 minus a negative 5. In the denominator, we will have 10, we already see that. For g of 5, we're calculating the area of this triangle, which is 1/2 times 2 times 4, which is going to give us 4, plus the area of this rectangle, which is 4 times 2, which is 8. 4 plus 8 is 12. And now we're subtracting the g of negative 5. So we're calculating this triangle, the area of this triangle, and the area of the semicircle and this little triangle. So here we have 1/2 times 3 times 4. That is 6. The area of this triangle is 1, so that's 7. And then the quarter circle is 1/4 of pi r squared. 1/4 times 4 pi, that's pi. So we get area 7 plus pi. So we subtract. Our answer to part A is going to be 5 minus pi over 10. For part B, we're looking for instantaneous rate of change of g, so we're looking for g prime at x equals 3. G prime at x equals 3 is just going to be f of 3. So we're looking for f of 3, and f of 3 is going to be equal 4. So this coordinate is 4. That's part B. Part C is about concavity. Our graph of g is going to be concave up, where the function f is increasing. So the derivative of g should be increasing. So the function f is increasing on this interval and this interval. So from negative 5 to 2, our graph of g is concave up on intervals from negative 5 to 2, negative 2, and from 0 to 3. When the question says justify your answer, it's important to add something to this. We cannot just say graph of g is concave up. We have to explain why. And our explanation is because g prime, which is f, is increasing on these intervals. Because g prime of x is increasing on these intervals. Now that looks like an acceptable answer. To figure out where our function g has a critical point, we have to think about the derivative of g, which is f, that is equal to 0. F of x equals to 0 and x equals negative 2 and 1. Because we're looking where g has a critical point, g prime is f of x. That means that we're looking for f changing sign. F changes sign at 1, it does not change sign at negative 2. So at x equals 2, we have neither. And at 1, f changes sign from negative, it was negative here, it became positive. So our function has f is negative, f is positive. So graph g has a local minimum. On a p-test, when the question says justify your answers, that means that a portion of your grade, of your score, is going to be towards that justification. So saying at x equals negative 2, there is neither, and at x equals 1, there is local minimum, it's not going to be enough. You will get partial credit, but not all the credit. You actually have to write out why, because g prime changes sign from negative to positive, because g prime does not change sign. So this is question number 3. This problem gives us a table of values, tells us that it's known that the value of the function at 0 equals 20. The first derivative satisfies this inequality. It's between 0 and 7 for all values of x in our interval from 0 to 6. We also know that the function has continuous second derivative for all real numbers. We need to calculate the midpoint Riemann sum with 3 subintervals of equal length to approximate f of 6. Then we have to answer, can f of 6 actually be equal 70, and explain that. And then we're calculating the integral from 2 to 4 of the second derivative of f of x dx, and then we are evaluating this limit. So to answer the first part, we're calculating, approximating f of 6. We will evaluate the integral from 0 to 6 of f prime of x dx. we have to have 3 subintervals, so each subinterval is going to have length 2, but we're looking into the mid sum, so we're looking at the middle number of that subinterval, so 3.5, 0.8, and 5.8. Those are middles of our intervals. So 2 times 3.5 plus 2 times 0.8 plus 2 times 5.8. That's going to be 20.2. But this is, according to the fundamental theorem of calculus, the value of f of 6 minus f of 0. We do know that f of 0 equals 20. So 20.2 equals f of 6 minus 20, which tells us that f of 6 is going to be 40.2. For part B, we're again looking at our integral of f prime of x dx. We know that f prime of x is going to be less than 7. So this guy is going to be less or equal to, is going to be less than or equal to 6 times 7, which is 42. Our integral is f of 6 minus f of 0, which is less than or equal than 42. That tells us that f of 6 has to be less than or equal than 42 plus f of 0, which is 20. F of 6 has to be less than 62, which tells us no, f of 6 cannot be equal 70. For part C, we're calculating the integral from 2 to 4 of the second derivative of x dx. Fundamental theorem of calculus tells us it's antiderivative of the second derivative, which is first derivative at 4, minus the first derivative at 2. First derivative at 4 is 1.7. Okay, those are values of f prime, minus the first derivative at 2, which is 2, and we get negative 0.3. For part D, usually when on AP I'm asked to calculate the limit, I'm being suspicious. I think that probably we have to use the L'Hopital's rule. It's not that easy. Or even if you just try to plug in x equals 0, f of 0 is 20. Okay, 20 minus 20, that's 0. So we have our undetermined form 0 over 0. And we have to use our L'Hopital's rule. So let's calculate the derivative of each one of those. So we have f prime of x minus 20 e to the x, and then we have 0.5 f prime of x. Now f prime of 0, that is now 4, so now I have 4 minus 20, and 0.5 times 4, that is 2. 4 minus 20 over 2, negative 8. In our problem 5, we're given region R that is bounded by graph of square root of cosine e to the x, and then the vertical line that goes through x equals pi over 2. First part is asking us to just find the integral expression for the area of R. That's it, we don't need to calculate it. We can see that our graphs, they intersect. We just calculate the area by subtracting the area under this curve, which is e to the x, minus the area under this curve, which was cosine of x. And this is happening from 0 to pi over 2. And in this case, you have an option. You can either explicitly write down e to the x minus square root of cosine of x. That is your area. Or you can just write down g of x minus f of x. That is okay to do on the test. For part B, we need to find the volume of the solid generated when R is revolved about the x-axis. So like this. Because the solid is generated by revolving around the x-axis, we will be using our washers method. We have a little bit of a hole in there. So we will be thinking about area of a circle. Area of a circle is pi r squared. So we will be calculating an integral. So the volume is going to be integral pi. And then pi is the constant, we factor it out. And then the integral is r squared. What is r squared? That's our g of x squared minus the second function, which is square root of cosine of x. And that has to be squared. Our integral goes from 0 to pi over 2 dx. From here we simplify. We have our e to the 2x minus cosine x dx. And those are our table integrals, so that should be easily done by hand. All is left for us to do is plug in pi over 2 and pi. Pi over 2 e to the pi minus 1 half, that's minus 3 over 2, so minus 3 pi over 2. That's our answer to part B. For part C, we need to find the volume that is created by cross-sections. Our cross-sections are like this. Region R is the base of a solid whose cross-sections perpendicular to the x-axis. So they go like this, down, perpendicular to the x-axis, are semicircles with diameters on the xy plane. So they look somewhat like that. So diameters are on xy plane. We need to write an integral expression that gives the volume of the solid. It also usually specifies write, but do not evaluate. So we're just writing down that expression. Because our cross sections are semicircles, we are again thinking about the area of a circle. Area of a circle, pi r squared. The radius is going to be half of this diameter, and diameter is the difference of g minus f. And then we need to calculate half of that because it's a semicircle. So let's put all of this together. So volume 1/2 integral from 0 to pi over 2. Okay, now we're thinking about, so that's half because it's a semicircle. Pi r squared, so we have pi, or I could factor it out. R squared is our g of x minus f of x over 2 squared dx. So once again, this is the diameter over 2, that's the radius, pi r squared, and then we're adding them up, and we're calculating half of that because we have semicircles. That is it. In problem 6, we are given a description of what's happening on the computer screen. There are two circles that start at dots, and then they start expanding. At the instant that the first circle has a radius of 9 centimeters, the radius is increasing at a rate of 3 over 2. So I know already that radius is 9 and dr dt is 3 over 2 centimeters per second. Find the rate at which the area of the circle is changing at that instant. I know the formula for the area of the circle, which tells me that now because I'm looking at the rate at which the area is changing, I have to calculate the derivative. So this is a classical related rates problem. I'm calculating the derivative of both sides with respect to t. Calculating the derivative of r squared, that's 2r dr dt. Remember that part. We do know r and we know dr dt. Let's plug them in. Once we plug in our numbers and simplify, we're going to get 27 pi. That is centimeters squared per second. Look at this. The problem says indicate units of measure. That means that one point goes towards the units of measure, and you must indicate them. That also means that if you're lost and you don't know what the question is going to be, just write down the units, and at least you will get 1 point. In the second part, we're given the radius of the circle is described by this expression. W of t is measured in centimeters, t is measured in seconds. At what time is the radius increasing at a rate of 3 centimeters per second? So the radius increasing at a rate tells us we need to find the derivative of this expression. Let's simplify. We get 6 e to the negative 0.5 t. We calculated the derivative, simplified it, and we are given that the derivative changes at a rate of 3 centimeters per second. So we set it equal to 3. Let's solve this equation. We calculate natural logarithm of both sides. Remember, ln of 1/2 is negative ln 2, so our negatives will cancel out, and then I can multiply by 2 to cancel this. Once I simplify, I get the time is 2 ln 2 seconds. It's a non-calculator question, so obviously we cannot simplify this. That is a good, legit answer that is going to give us a point. In part C, we are given that the model for the radius of the second circle is given by some function. Function measured in centimeters, t is measured in seconds. The rate of change of the radius is given to us. And the question says, based on this model, by how many centimeters does the radius of the second circle increase? So how does the radius change? We have the rate of change of the radius. And now we need to say something about the radius. So what do? We undo the derivative, aka we calculate the integral. The integral from 0 to 6 of t squared minus 4t plus 4. We anti-differentiate our f prime of t. This is, again, straightforward table integral. We calculate the antiderivative, we simplify, we get 3. So our answer is the radius of the second circle increases by 3 centimeters from 0 to 3 seconds. I hope this was helpful. Follow me for more calculus, and I will see you next time.